Now, from the generalization point of view, this is a very interesting setup. So the idea is, if you take a continuous function f from R to R, this function is continuous if and only if we take inverse image of open set from here. So inverse, if we take a G here, inverse of that is also open. So this is a useful property. And in fact, when you're doing topology where you don't have access to the elements inside, you define a function to be continuous. So let me just briefly digress on that, not necessary for our course, but so f, a function from x to y between two topological spaces is open, sorry, is continuous if f inverse of u is open in y, sorry, in x for every u open in y. So inverse image of every open set is open, then we call the function to be continuous. That is a definition of continuity in the topological space perspective. But for now, for us, it is just a consequence. Another consequence of this discussion is there is a concept of subspace topology. For example, if your space itself is, say, 0, 1. Again, these are the things not related to our course, but I think they are important to mention how they fit in the bigger picture. So suppose your topological space is just 0, 1. Yeah, not whole of R. In this space, 0, 1 is open, right? Because the whole of space is always open. All right. So this actually, you should, if you're really interested in analysis at the moment, you should look at the subspace topology and see what is happening around there. Okay. Anyway, coming back to our course. So now we want to understand some properties of continuous functions. Namely, what are the properties of a set does the continuous function preserves? So for example, if f is continuous, D is bounded, then is f of D bounded? Right? A question like that. Or if D is closed, is f of D closed? Okay, so these are the important questions one should answer regarding the continuity. So first of all, the first part is not true. So D is bounded does not gives that f of D is bounded. And the classic example for that is take f of x equals to 1 over x on, say, 0, 1. So this set is bounded, but so this is bounded, right? This is your D, but f of D is going to be what? 1 to infinity. So this is not, right? So f of D is unbounded, all right? So in fact, we can have a definition of a function being bounded. So f from D to R is called a bounded function if f of D is bounded. So that's the story, right? So similarly, you can think about if D is closed, is f of D closed? So that's a good exercise to think. So one should ask the questions, what are the properties of D which are preserved under function, continuous function f. So here is a interesting property, which is namely following theorem, which is 5.3.2 in your text. It says if D is compact, and f is a function from D to R, continuous, then f of D is compact. Okay. So how do we go about the proof of this? So you start with an open cover. So start with the open cover of of f of D. So let's say let G be Gi, oh sorry, we don't want to use I, we'll reserve that for finite ones. So let G alpha belong to some indexing set, we don't care, be an open cover for f of D. Now what do you want to do? We want to produce a finite subcover, right? So now what we're going to do is we are going to take open cover for f of D, pull it back. So here's the idea of the proof. You have f of D here. This is f of D. You pull back, so you have open covers, infinitely many of them. I cannot draw them, but you pull it back here to your D. This will be open cover for, this will form an open cover for D, which is, so since D is compact, there'll be finitely many of them covering, and then send them back. Okay, so that's the idea. All right, so let's try to write down this idea. So we want to show that, to show that G admits a finite subcover. Now, since f is continuous, since f from D to R is continuous, we'll use the property of continuous function that if you take an open set, you can pull it back to an open set H, which is here. So if you take a continuous function f from D to R, which is continuous on D, then what happens, you can, for every open set here, you can pull it back. If you take f inverse of G, it will be D intersection some open set in R. Okay, so we'll pull back each of this. So f from D to R is continuous. So let's pull back each of these open sets. For this guy, there exists H alpha in R open such that what? H alpha intersection D equals to your f of inverse of G alpha. Yeah, so this is guaranteed because of the continuity here, right? So now note that, first of all, your f of D is a subset of G alpha. This would imply, sorry, union of G alpha and I. This implies your D is a subset of f inverse of what? Of G alpha union. Union of f inverse of G alpha. Yeah, so these kind of inequalities you should prove from the set theory, that if you have f inverse of U G alpha, that is same as union of f inverse of G alpha, and you take the union. Okay, this is not true for intersection though. Okay, so is this true? Show that this is not true for intersection. What is not true for intersection? That F inverse of intersection of G alpha is not equal to intersection of what? F inverse of G alpha. Yeah, because this could be empty, right? G alphas could be empty, whereas you can have it in a way that this is non-empty. Yeah. So this is not true. However, for union, this is good. So we have that D is contained inside this F inverse of G alpha, which are, and so we have D is contained inside union of F inverse of G alpha, which is subset of union of H alpha intersection D. Well, this is equal, but which is contained what? Which is contained inside union of H alpha in R, right? So there, but D is compact, right? But D is compact implies there's an, so this is an open cover, right? So that is union of H alpha. Let me write that down as well, so that, so we have H alpha, alpha in alpha, alpha in I is an open cover for D, and since D is compact, it admits a finite subcover, a finite subcover. Now let's call that subcover. So let's call that subcover as, let's say, H of alpha 1, H of alpha k. This covers what? Covers your D. Yeah. So that is your D is a subset of H alpha 1 union H alpha k. Take intersection with D on both sides. So this is going to be H alpha 1 intersection D union H alpha k intersection D, right? Because I want to basically get back to my F, but get back to F of D, and that I can only get through basically H alpha I intersection D, right? That's the connection here, H alpha intersection D. Yeah, so this implies that is same as saying F of D is contained inside. But what are these guys? These guys are, so H alpha intersection DI is F inverse of what? G1 union G2. This is F inverse of G1 union F inverse of G2 dot F inverse of HK intersection, sorry, F inverse of GK, right? Because we have H of alpha intersection D, H of alpha intersection D is F inverse of G alpha. So if I'm labeling them as alpha I, so this is going to be F inverse of, maybe the proper labeling would be alpha I, sorry. Yeah, that would be the proper labeling, alpha K. Okay. So this would imply that F of D is contained inside G alpha 1 union G alpha K. So therefore you have shown, so therefore G alpha I going from 1 to K is a finite subcover for F of D. Therefore F of D is compact. Okay, so that basically does. Okay, so you have F, a function from, let me see, there's some more questions after. F is a function from D to, then F attains. So it attains extreme values. That means it has local, it has absolute maximum and absolute minimum, right? This is also a variation of in Calc 1, you would have seen the result that if you take a continuous function on a closed interval, then it has absolute maximum and absolute minimum. Yeah, the closed interval is the version of compact, right? Its closed interval is compact, right? So closed and bounded interval, my bad. Oops. Okay. All right. So let's continue with this now. Oops, what happened? Attains. Yeah, that's right. Somebody is basically okay. So this is because of the following. So this is the consequence of the previous result. Actually, it should be called a corollary because it's not really a full theorem. It's a consequence of the previous one. The idea is that if you look at f of d is compact, yeah, because of the previous result. So now f of d is compact. So recall we had this result that if d is closed and bounded, then d has, so if we have d is if you have a function d which is so if you have d is closed and bounded, then d has maximum and minimum inside d. Yeah. Now note that this is a maximum of a set. So largest value of this set, because all of our all of our all of our sets are in real numbers instead of real numbers, and real numbers we have ordering. So with respect to that ordering, we are saying it has maximum and minimum element inside D. So similarly, f of D is compact. Therefore, you can find out a maximum element in f of D, which will be the absolute maximum of your function. And you can find the minimum element of f of D as a set, which will be the absolute absolute minimum of your function. Okay, so from there you can basically make it out. Okay, so clearly again this doesn't this breaks down when you have D to be any open set, right? So f does not attains max or min. Okay, so yeah, they are same thing. Absolute max or max are the same thing. You do not give the adjective, you only give adjective to local max. All right, so absolute maximum and maximum are same. All right, so now we want to prove the following lemma. Now our goal is to move towards the intermediate value theorem. So lemma, if you take a function f from a closed interval a, b to r, and this function is continuous, and suppose you have f of a less than 0, less than f of b, then there exists a c in AB such that f of c equals to 0. Okay, so you have the following, you have f of a, you have f of b, then you're hinting that there is something at which the c becomes 0. So the idea is the following, you basically take all the elements here, so take all x such that f of x is less than equal to 0. So you take all the x such that less than equal to 0, and this set will have, look at the supremum of this set, and this supremum is, so let this supremum be, let C be the supremum of this S, and then show that, then show that f of c is 0. Okay, so this is a strategy. We can basically look at this and try to prove it. All right. Okay, so proof. You have to use law of trichotomy. Basically, try to prove it using saying the following: that if c is not 0, then c. So suppose if c is less than 0, then you can basically build a neighborhood around it, in which you will still the supremum property will be violated, right? Okay. Yes, is AB's, yeah, every closed interval is bounded. Closed and bounded, well, I mean, every interval of form AB where A and B are real numbers is bounded, right? Because it's, yeah, exactly, because of being closed and bounded. So therefore it's compact, right? Anyway, so let's move ahead. So using this lemma, you can prove what is called as intermediate value theorem. So intermediate value theorem tells you the following: if you take a function f from AB to R and it's continuous, then for any n in between f of A and f of B, there exists a C in AB such that what? Such that f of C equals to n. So the idea is you have AB, you have a continuous function on this. This could be one scenario, or it can be going down, doesn't matter. It can be like that. If you take any n, if you take any n in between here, there exists a C in AB such that f of C equals to n, right? So how do you prove this? I mean, this was given to you when you were doing Calc 1, but how would the proof go, particularly from the previous lemma? I mean, lemmas are generally a short helpers to the theorem. So how can we use this lemma? So let's start with the following. So without loss of generality, let f of A be less than f of B. Okay. So now what you do is you define a new function g. So you want to convert this into, so you want to convert this f of c equals to n to some function where it becomes 0, right? Because for that we have this guy. So I'll consider the function g to be g from AB to R again. And I'll take g of x equals to f of x minus n. Now clearly g is continuous. G is also continuous. G is continuous on AB as well, right? Because of the algebra of continuous function. I mean, you don't need to write that down. It's clear that you take a constant function and subtract from a continuous function, you'll still get continuous function. That's a very, so G is continuous, all right? And what do we have? We have G of A equals to f of A minus n. Now note that n lies in between, right? So n is between f of A and f of B. So in that case, what do we have? We have this is going to be less than 0. Similarly, g of B equals to what? F of B minus n. And since n is in between, this is going to be greater than 0, right? Therefore, by previous lemma, there exists C in AB. Why open interval AB? Because, well, because n is in between, right? So if you go back to the previous lemma, it says that C is in AB, open interval AB, such that f of C is 0, right? So we get by previous lemma, there exists a C in AB such that G of C equals to 0. that is f of c minus n equals to 0 or f of c equals to n. And there you go, you're done. So the next thing we want to discuss is the following. So there is another theorem which is kind of pretty straightforward. So if I is a compact interval, that means basically I is of form AB, right? Then f of I is compact interval with what? With where f is continuous, right? If f is continuous. If f is continuous. So there is a little bit of work required though here, all right? Because I is an interval, right? So I is a compact interval. Our previous result tells us that f of I is compact because I is compact. I is compact implies f of I is compact, but it doesn't tells you that it's an interval. Yeah. So for interval, you need some more work to do. Okay. So that you can work on that. Okay. So to show that f of I is also an interval. Okay. So that you have to basically, so you have to combine intermediate value theorem. Okay. So, all right. So this takes care of the continuity aspect. Now, let's move on to the next part of the discussion, which is uniform continuity. Now, before we go to uniform continuity, is there any reason for studying it? Why do we basically care about something more than continuity? Well, first of all, continuity is not that nice. Why? Well, continuity does not preserve a lot of things, right? It did not preserve if a set is bounded, then the image was not bounded, right? So we want a slightly more better notion of continuity. Of course, we can't call it continuity, such that the bounded sets go to bounded sets, right? So for that, we have the following definition. So let f be a function from D to R. We say f is uniformly continuous on D if, again, the story is same, given epsilon greater than 0, there exists delta greater than 0, such that what? Such that x minus y less than delta, x and y in D imply f of x minus f of y is less than epsilon. All right, so it looks quite similar to the definition of continuity. However, it is not. The reason for that is the following. What was a definition of continuity? Continuity was defined at a point C. Here, you're not defining it at a point, you're defining it on the set D. You're talking about continuity on a set. All right, so it says the following, that it is uniformly continuous on D if no matter what x and y you choose from D, as long as the distance between x and y is less than delta, f of x minus f of y is going to be less than epsilon. So this is more of a global phenomenon. Global in the sense global on D. Okay. In mathematics, we loosely, I mean, like at this moment, we can loosely throw this word, but it'll become clearer as we move ahead. So the uniform continuity is more about global phenomena. It doesn't depend on your point C, whereas continuity is a local phenomena, right? So let me just write down the definition of continuity so that you can compare. Let's use a different pen. Let f be a function from D to R. F is continuous on D if f is continuous at every point C in D. So you see, you do not talk about continuity without appealing to the point inside D. All right. So, and that is given epsilon greater than 0 and given C belong to D, there exists delta greater than 0 such that what happens? X minus C less than delta implies f of x minus f of C is less than epsilon. So you see, your delta is basically dependent on the C, yeah, delta C, all right? So although I'm not writing it here, but it is clear that it depends on your C is already chosen to start with, okay? So this is the difference between continuity and uniform continuity. So let's do some problems so that things become more clearer. So first of all, so example 1 is an example of a uniformly continuous function. So let's say f of x equals to ax is uniformly continuous on R. Yeah. So how would we go about it? We can say, well, we want what we want, f of x minus f of y. So let's just work this in the side. So, you know, rough work, whatever you're gonna call it, scratch work, rough work. F of x minus f of y is going to be ax minus ay. And this is going to be absolute value of a times x minus y. Yeah, so without loss of generality, a is not 0. If a is 0, then it's uniformly continuous right away, right? So let's basically, and we want this to be less than epsilon, that is x minus y is less than epsilon by a. Yeah, assuming that a is not 0. If a is 0, then it will work right away. You don't have any epsilon and delta will work, right? So we have this. So this should be our choice of delta. You see, we haven't appealed to any particular point in this case. So let's look at this. So let's write down the proof now. So given epsilon greater than 0, delta equals to epsilon by a, absolute value of a. I will basically impose here a not equal to 0 so that there is no case of chance of confusion, is such that moment your x minus y is less than epsilon by a, which is my delta, what do I get? I get f of x minus f of y, and this from the above I can see is going to be absolute value of x minus y, and this is basically, this thing is less than epsilon by a, and we get this is, well, this is equal to epsilon, but the whole thing is less than epsilon. Yeah, this whole thing is f of x minus is less than epsilon. So therefore you have proved the following. So what we have proved, therefore f is uniformly continuous on R. Now, what is the idea? If I want to look at this pictorially, what will happen? Let's see. Of course, I can't draw a random ax, but let me just draw f of x equals to 2x, say. So 2x, 1, 1, 2, 3, 4, 2. So 0, 0, 1, 2, and 2, 4. Right. So now if you take x and y in certain width, if you look at the intervals, if you look at the distance between x and y here, or say let's take x and y of a width here, the same width here, if you look at distance between them, loosely speaking, the width of f of x and f of y is also maintained. All right. So therefore, this function is uniformly continuous. Now, let me give you an example of a function which is not uniformly continuous. To take f of x equals to x squared on R. Now, the problem is, so why this guy is not uniformly continuous? Let's draw this. Okay. So 1, 2, 3, 4. Okay, so somewhat like that. So now, if you look at the width here, then the widths get translated like that. But if you look at the same width here, the width kind of should draw it properly. So width kind of blows up, right? And the further you go, the width kind of becomes larger and larger. So this is no longer true. So what is the meaning of this? The meaning of this is here you may have x minus y less than delta. Here also you have x minus y, all this x minus y less than delta, but the difference, the moment I move it further and further away, the distance between them is gonna increase, right? So it is not uniformly continuous. So let's prove this. So what does it mean by a function not being uniformly continuous? So let's give that definition first. So what do we want? We want negation of this statement here of uniform continuity. So this means what? There exists epsilon greater than 0, epsilon, not delta, epsilon greater than 0, such that for every delta greater than 0, x minus y less than delta implies, sorry, we have x minus y less than delta, but f of x minus f of y is greater than equal to epsilon instead of being less than epsilon. This is a negation of, this means what? Not uniformly continuous. And also here, I mean, like, I should keep writing this all the time. You should, please, x and y should be in your set D, all right? I mean, if it is not in the domain, then, well, so this is what we want to get at, right? So let's see, let's investigate this. So what does f of x minus f of y looks like? So f of x minus f of y is going to be x squared minus y squared. This is going to be x plus y. Sorry, what is wrong with this guy? X plus y times x minus y, right? So we want to basically say that, well, for every delta less than this, so if x minus y is less than delta, this guy can blow up, right? This guy can be really very big, right? So we'll choose the following way. So let epsilon be anything you want. In particular, let epsilon be 1. Yeah. Then for this, so what we have is, we can have, let's take x, so x minus y less than delta. We want basically x and y such that x minus y is less than delta, but what, f of x minus f of y is bigger than equal to 1. You'll say, why did you choose 1? I chose 1 arbitrarily. You can modify it to whatever, all right? All you have to do is modify the choices of. So now this is what is basically causing the blow up, right? So let's see. So if x minus x plus y upon delta is less than epsilon, right? This is what, so if this is less than delta, then what will happen? X plus y delta is less than epsilon. So we should choose x equals to something. So x, so that difference between x and y is still, so we want that difference between x minus y is still less than delta. But if you look at f of x minus f of y, in particular, x plus y times delta is greater than 1. This is what we are looking for, right? So how do we go about it? Let's choose, so we can make a choice of let y be x, sorry. So I'll choose x equals to y equals to x plus, so I want this to be, I want somehow, I want basically, I want delta in the denominator so that it can cancel out, right? So let's take x equals, so y equals to 1 by delta, okay? I'll modify it if need be. So let's take x, y equals to x1 plus delta. So what do we have? We have, sorry, we want, my bad, we'll take y equals to x plus delta. We need x minus y is less than delta. So we should take maybe delta by 2 or delta by 3. So let's take x to be delta by this. So in this case, we have x minus y less than delta, right? Okay. So now what we do is the following. So we have x minus y less than delta by 2, which is delta. Okay. Now we should choose, so we should choose now, if we choose x carefully enough, we can make x plus y blow up, all right? So that it can cancel this delta. So let's take basically x to be 1 by delta. Let's see. So we get what? I'll have to modify this a bit. So let's see. X plus y is going to be 1 by delta plus delta by 2 times delta. This is going to be bigger than, because these terms are positive, right? This is going to be bigger than 1 by delta times delta, which is 1, right? So x equals to 1 over delta does the job, right? So let's write this result nicely down now. So given epsilon equals to 1, choose x equals to 1 by delta, y equals to x plus delta by 2 is such that x minus y is less than delta, but what do we have? F of x minus f of y. Now that is going to be x squared minus y squared. That is going to be bigger than equal to what? X minus y times x plus y. This is going to be x minus y is, so this is x plus y is what? X plus y, which is bigger than 1 by delta times delta, which is bigger than 1. So therefore, f is not uniformly continuous on. Okay, does that make sense? Yeah. Right. So resume. Okay. So now you notice that f is not uniformly continuous on R, but so this is similar to what Ari's comment was, that that it is the slope is unbounded. However, if you consider the same function f of x, so let's look at the following function. Let me change the pen. So let's take f of x equals to x squared on an interval a b, then basically f is uniformly bounded. Okay, so I will work with an example. I mean, like we can basically look at particular choice of how things should be when we look at the example 0, 1, and then we'll. So what we need is f of x minus f of y is less than equal to we have x square minus y square. Actually, it is equal to this. This is going to be x plus y times x minus y. Now, all you need is that if this is bounded, right? This is bounded, then what happens? Say, this is going to be less than equal to what? You are in the interval 0 to 1, so this is going to be less than equal to 2 times x minus y. So given epsilon greater than 0, there exists delta equals to epsilon by 2, such that moment you have x minus y less than delta implies f of x minus f of y is going to be less than equal to 2 times x minus y, which is less than epsilon, right? I mean, like less than equal to epsilon, but the whole thing is less than epsilon. So you see, in this case, you can use because the interval is bounded, you can find the bound on that. Okay, so this is similar to, recall the mean value theorem, although it's funny because we have to discuss mean value theorem at some point. We had f of x minus f of y is less than equal to f prime alpha times x minus y. We can, is equal to, if you look at this guy, this is a variation of your mean value theorem where x and y and alpha are constants. Yeah, they're not variables really. But essentially you are, if you take all x and y, you can show that if the slope is bounded, then you can prove that it's uniformly continuous. Okay, so anyway, so question is, when is the, so here you saw f was continuous from D to R, is continuous. Moment there's something special about your D, f became uniformly continuous. So what is that special thing? So if D is compact, then f is uniformly continuous. Right, so let me give you a few examples. Why is that the case before we go on to look at it from a general perspective? So note that if you took the original function, sorry, all right. So if you take a D, a compact set, and f from D to R is continuous, then f is uniformly bounded. So let's look at few examples along this line. So first of all, just f being a function from D to R is continuous, if f is a function from D to R and is continuous, let's say if D is bounded, then consider f of x to be 1 over x on 0, 1. Yeah, uniform continuity does not hold here. Right? However, in some cases it will hold. For example, if you take f of x equals to x square, it was not uniformly continuous on whole of R, but on 0, 1 is uniformly continuous. The point of this statement is that just if D is bounded, this is not enough to show that it's uniformly bounded. Right? If D is just closed, then of course it is far from being true, because your D can be R and it's closed, right? This is a closed set, but of course, clearly f of x equals to, this is closed, but f of x equals to x squared is not uniformly continuous. So you need closed and bounded both, and this is what the result is. If D is compact, then f is uniformly continuous on D, of course, right? I mean, like, you have to mention the domain. All right, so how do we prove that? Yeah, that is the point, right? So let's try to approach to the proof. So proof. So proof of what? Proof of this guy here. So now note that it's a continuous function on your domain. So the idea is we have continuous function on your domain D. So continuous function, so we'll construct the continuity for each of the interval at D. So the idea is the following. So suppose this is your domain D. The function is continuous. So that means the behavior will be all right in some open interval like that. In some open interval, it's gonna behave as if like it's a uniform continuous on those intervals. And then you argue that there are finitely many which cover this D, and then from there you can carry the uniform continuity over. Okay, so that is the idea behind this. So let's prove that. So let epsilon greater than 0 be given. For this epsilon greater than 0, we want to prove the uniform continuity. All right, so this is a starting point. Now, f is continuous at, so at x belonging to D, if what? If for given epsilon greater than 0, there exists delta greater than 0. Of course, this delta depends on x. So now I will write down delta x such that I have x minus y less than delta x implies f of x minus f of y is less than epsilon. Of course, we'll modify this delta x, and so we'll modify this epsilon. Maybe we need epsilon by 2 or epsilon by 3. We'll see that later on. But so this is a story. All right, here it may be slightly, the notations are slightly different. All I'm doing is instead of c, I'm using x, and instead of x, I'm using y. Right? In the usual continuity definition, you have x minus c less than delta, right? So instead of constant c, I'm using x, because you see x is continuous at x belonging to D. So this should not be seen as a definition of uniform continuity yet. So let me just make a point. So let epsilon greater than 0 and x belong to D be fixed. Right? Because uniform continuity allows you to choose any x and y which are in difference at difference less than delta, right? So we have this. Now, what we'll do is the following. Consider all this n x delta x. Again, I'll modify this neighborhood depending on what I need, but consider this n delta x, and let's take union of this x belong to D. So this will clearly cover your D, right? Because essentially at every point you're building an open neighborhood. So this will cover your D, this imply, but D is compact, right? But D is compact. So this implies there exist x1 up to xn such that what happens? Such that your D is contained inside union of I going from 1 to n of n delta xi of xi. Yeah, this is consequence of D being compact. Okay. Now take your D delta to be minimum of delta x1, delta x2, delta x. Now this is a delta or some multiple of it will work for this delta will work for uniform continuity. Let's see why. So suppose x and y belong to D and x minus y is less than delta. Now this would mean what? This would mean that x belongs to some of these, right? Delta xi of xi, right? I mean, like, because it's an open cover after all, so one of the delta xi will basically contain your x. Now this means what? This means that the distance between x and xi is less than delta xi, right? But this would imply what? That f of x minus f of xi is going to be less than epsilon, right? This comes from the continuity at xi. So far good. Now, similarly, what do we have? We have y minus xi is going to be less than y minus x plus x minus xi, right? So now y minus x is less than delta. So it's going to be less than delta xi. This guy is less than delta xi, which is 2 delta xi. Yeah. So this would imply f of y minus f of xi is going to be less than. So I have to modify this, right? So I will modify this back now. We'll take epsilon by 2. So delta by 2, delta by 2. I'll go back and modify it. All right. So this is what your textbook does as well. But I don't want to, I didn't want it to include them to start with so that you see when do you have to go back and modify. So this is going to be less than epsilon. Now let's look at f of x minus f of y. This is going to be less than f of x minus f of xi plus f of y, sorry, f of xi minus f of yi, sorry, y, my bad. Because of the triangle inequality, this is less than equal to, sorry, this is strictly less than epsilon. This is strictly less than epsilon, which is equal to epsilon. So not only that, we had to also modify this to be epsilon by 2, epsilon by 2. So epsilon by 2, epsilon by 2, epsilon by 2. So this will basically work. So this is the the idea behind the uniform continuity. So the proof lies in the fact that because your domain is compact, you can create a open cover for D in which each of the cases there will be some kind of a uniform continuity, and you add all of them up. Your question, and we'll solve your problem. So the next thing is the following. So if you take a function, so another bad thing about continuous function is the following. So you take a function f from D to R, and you basically, so this function is, so if xn is Cauchy, then f of xn need not be. So xn is Cauchy, so you have f is continuous, xn is Cauchy, there exists a sequence xn is Cauchy, then f of x, and we have and f of xn is divergent. So basically, the idea is if you take a continuous function, it cannot preserve even Cauchy sequences. All right. But you'll say, well, this seems to be not true because we have the idea of sequential continuity. If xn converges to x, then f of xn converges to f of x. This is only true when x belongs to D, right? If x does not belongs to D, which is our example, now we will basically show that for that problem. So if x does not belongs to D, we can construct such an example. Do you have an example in your mind which would work? So that xn is Cauchy, but f of xn is divergent.